Okay, excellent, it works. Okay, shall I start? I think so, no? Yeah, everybody's here. Okay, thank you for bearing with me, and that's the very last lecture of your training week. So now we talked about a bit of the motivation and proton modeling QCD. We talked about collinear factorization, and then you already had an intuition that this is a kind of a complex machinery. Even just trying to think about all the experimental data, disentangling all the constraints that you get from the different experimental data, and so on. So now I want to talk about, in this last lecture, the statistical framework, because it's very important to understand what is inside the PDF fit, and then a bit about the theoretical calculation and the challenges. So methodological aspects. So if you think about it, it's quite of a complicated game, because if you want to determine a single quantity experimentally, so you have to give a 1 sigma error, so 1 standard deviation. If you have multiple quantities, you've got this multidimensional contour, but you want to find a function which is a 1 sigma error band in a functional phase. Okay, so this is more complicated. What you want to find, if you want to find a function and the error, you want to find the probability density in the functional space of the function you're trying to determine. Okay, so in a sense, all the expectation values are functional integrals. So that's what you want to find. So if you have an observable that depends on a function, you want to integrate over the functional space by weighting over the probability density in that functional space. And you can see that this is clearly a kind of ill-posed mathematical problem, because you have a finite number of experimental data, and you want to find an infinite object, such a function, from a finite number. So you have to do some approximation, and these are crucially in kind of determining what we are doing. Indeed, imagine just a very simple toy model. So imagine that we have a set of uncorrelated measurements of a quantity. So it's even simpler than PDF. You directly measure the quantity that you want to then extract from the data. So this is measured at different axes, and imagine they're uncorrelated. And the underlying law that nature established for this quantity is a sign function, but we don't know about it. So we try to guess it with the fit, okay? So this is the game. That's actually something, it's in some Python notebook that I have somewhere. So very good. So first of all, you have to choose a figure of merit. So you have to choose a kind of parameterization for f of x. In this case, I chose a polynomial, okay? So you can add several degrees to a polynomial, and you want to perform a fit by minimizing a function, which we call a figure of merit, whenever you have to find the minimum, which we can define like the chi-square. So it's the log likelihood to the data, okay? So di is the data calculated at these different points in x. Ti is the theoretical prediction that you get with a given functional form, and sigma is the uncertainty of these data points, okay? Because they're uncorrelated, so you don't have any correlation matrix, it's simple. And if I start training my parameterization, actually here I did it with a neural network. So you can see that here, this is my fit, and these are the data. You're not quite there. And you see it because the chi-square per degree of freedom is much larger than 1. So this is an example of underlearning. When you're here, you have kind of learned your function, okay? So this is an example of proper learning. So you're going through the data with all the statistical fluctuation of the data. If I go too far with my training, I start fitting some of the noise of the data, okay? So I start having some jumps that don't have anything to do with the underlying law of nature. It's just the fact that I have a too flexible parameterization, so I'm overlearning the data, okay? And in that case, really the chi-square goes to 0, which is what you don't want to have. You want the chi-square going to 1 to have a proper fit, okay? So that's a kind of statistical statistics 1.0, but I think it's important to understand what we are doing, okay? So the point is that in this toy model, what did we learn? So we want to determine an error out of this fit, which is due to the lack of information that we get from these points. Clearly, in the limit in which we had an infinite number of experimental points and they all had an uncertainty that tends to 0, there would be a one single solution for this problem, okay? So you wouldn't have any functional uncertainty associated with your parameterization because you would have a single solution that goes through all these points if they were all perfectly compatible with the underlying law of nature. But okay, we know that data are not all spot on the law of nature. And we also know that in this case, we have a finite number of data, okay? So how do we determine this shaded 1 sigma contour in the functional space, okay? So this is what I'm going to talk about for real PDF fits in the next few slides. Is the problem clear? If you have any questions, ask me. It might be trivial for most of you, but I think it's important to understand it in these terms. Yes? Yeah, if you want to have a chi-square equal to 0, and you want to have an, this is what I did. I nearly did here. So if I had gone farther, I would have probably needed to go to higher orders in polynomials. At that point, with a sufficient number of parameters, you can go through exactly the central value of these data points. But you're not learning the underlying law of nature because data are noisy and you don't want to fit the noise of the data. Okay, so in this regard, we always have a bit of a preconception on how nature should work. We always think that natural laws have to be smooth. We don't believe that the wiggles belong. But now I will show you that there is a kind of less naive way of thinking in terms of what is a good fit, what is an underlearned fit, what is an overlearned kind of fit, okay? No, this is just a toy example. This is a toy example where I know exactly what is my underlying law, but you can also try this game with a more complicated law. I will show you later how to validate. Yeah, exactly. This is what, for example, the PDF fits that are based on fixed parameterization, which is what I'm going to show you in a few slides. They try to make it more flexible by using some Chebyshev polynomial basis or Bernstein polynomial basis. So there are some bases of polynomial that you can use in order to increase the flexibility of your parameterization, okay? But let me talk about it in a second, because that's exactly what I'm going to talk about. So the actual game is more complicated in that this was just a toy model, just an example to show that, already at this level, there are some problems that arise. And the actual game is because you want to fit is not 6, actually, 3 plus 3 plus 1, depending. So depending on how many flavor you parameterize at the initial scale and the gluon. And the errors to determine quantities that are not directly measured. You never measure exactly the function, you measure combination of function. Still, I think what we learn from this kind of toy game, you need to choose a clever and flexible parameterization, otherwise you don't get a good fit to the data. And you want to stop the fit before you overlearn the data, okay? And you don't want to fit the statistical noise. And you want to have a reliable error estimate. So an error estimate that gives an error that goes to 0 in the limit in which you have an infinite amount of compatible data that constrain that region in X, okay? So that's a game. So how do we do? So you want to, exactly, that's what I just said. One parameterizes independently the gluon, the light quark and anti-quark, the strange and anti-strange. Sometimes you can even parameterize the fitted charm, while the heavy quarks are generated perturbatively from gluon and quark. So you usually don't have a bottom quark intrinsically. You produce it at threshold, and if you go to FCC 100 TV, you might even produce a top, okay, it's borderline. Usually the top is never included in PDF fits. And the ideal parameterization doesn't have to be too rigid because the global fit might not have the flexibility to describe the data or might have inadequately small uncertainties where there are no data. If it's too flexible, it's difficult to minimize it, and it might develop some artifacts driven by statistical fluctuations. So this is the kind of paradigm that PDF fitters have in mind, okay? Good. And also remember that we are not completely free in our functional space. We do have some analytical constraints that come from the baryon number conservation that give us the valence sum rule. So we know that if you integrate over all x's at all scales, the integral of u minus u bar has to be equal to 2. And if you integrate over all possible fraction of momentum, the d minus d bar, you want to have 1 for a proton, okay? And also no intrinsic strangeness, okay? You want to have like s minus s bar integrated has to be equal to 0. And also you have from the momentum conservation, the momentum sum rule, which is what I was mentioning before. So if you sum up the fraction of momentum carried by all quark, anti-quark, and gluon, you have to get 1, okay? Very good. Okay, so how do we parameterize the independent function? So this Fi, I repeat, goes on the quark and the anti-quarks, okay? Typically the light ones and the gluon. So this is, for example, an example of a kind of parameterization that was used. I'm just taking one example of the pre-polynomial basis, MSTW 2008. As you can see here, you have some normalization constant. You always have x to some exponent because of the Regge behavior in small x, that we do have some idea on how the PDF behave when you're at small x, the old Regge theories. So again, it's not a theory, it's just a model, but we know that there should be some kind of x to some exponential behavior there. We know that the PDF have to go to 0 as x is equal to 1. So we always have a 1 minus x to some positive power. And then in between, you can do whatever you want, okay? So you can put up to any power of polynomials. So in this case, you can see that there are some square root of x and blah, blah, blah. But anyway, the function that you put there are kind of arbitrary, all right? And because of the sum rules that I mentioned before, not all of these parameters are independent. Some are function of the other because of the integral that you have to impose upon this parameter. I want to show you this extra term here because it's relevant for the example I'm going to do later. The possible issue is that, you know, if you fix the functional form, is what is the error associated to a given functional form? This is what John Pampling was showing at the beginning when we had the first CT10 fits. So he said, you know, this is your nominal uncertainty for the down quark, and this is the nominal uncertainty for the up quark. But actually, if I change the basis of the polynomial, I can get exactly the same good fit with this red line or with this purple line. So, and these are not included in your error band. So in a sense, how do you account for that, you know? And the other thing was exactly the term I was showing. So in MSTW, so this is the parameterization that I showed you before, they added this term. So on top of, you know, this x to the delta g, blah, 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 they added an extra term in the sum for the parameterization of the gluon. And this changed dramatically the behavior of the gluon at small x. As you can see here, the form without that extra term was not flexible. So it was really going down with a rather small uncertainty, even when there were no data. And as soon as they added this term, the uncertainty started to blow up, okay, in the region where there were no data. So it's very sensitive, you know, the choice of parameterization to the kind of nominal uncertainty that you have when you release these PDF set, okay? And these issues are there even now. In fact, that's why I think even the PDF collaboration that choose a kind of fixed functional form are moving toward more and more sophisticated polynomial basis. Because, for example, this is MMSHT, so that's the latest release. And you see, the gluon, they kept the same parameterization. But for example, they realized that they couldn't fit some of the new LHC data with the parameterization that they had for the U valence and D valence. It was too restrictive. So basically they had to add extra term to the polynomials. Otherwise, these data were not possible to fit, because now the curse is that the data are so precise that, you know, if you think you have a good enough parameterization, then you get some precise data and it doesn't go through these points exactly as you were asking. So, and as you can see, the new d-valence and u-valence are very different from the one you had before, but there is nothing, it's all a methodological thing due to the parameterization. So the ideal thing to do, which is what everybody is trying to do, is to have a flexible enough parameterization such that you don't have to add new terms to your polynomial when you add new data, because you would like to see that, you know, as you add new data, you decrease the uncertainty, okay, rather than having these shifts. So this is a tricky thing. The idea that's when I started to work on NMPDF in 2006, when I started my PhD, was, okay, because there were all this problem with the polynomials, we said, why don't we use neural networks? Because neural networks are these fancy tools that can actually that can actually interpolate any function. So in a sense, the good thing about neural network is that you don't have to have a polynomial parameterization. So the neural network can fit anything that you want. And this is what we did at the time. So there were about 300 parameters of the neural network versus 30 parameters in the polynomial parameterization. Again, the neural network is nothing magical. It's just, you can, so if you have a 1-to-1 neural network with one input, 2 neurons in the middle and 1 output, you can even write it analytically. Because I remember once I gave a talk about neural network and I was told, unless you can give me an analytical form, I will never believe in your method. So I figure it out for one particular activation function. You know, if it's simple, you can write it. It's just an ugly formula that depends on the activation function. But so it's not just to say that you could even write that. There is nothing magic about it. So, and at the beginning we had NF plus 1, 2NF plus 1 independent neural network. Now there is a fancier thing, but it doesn't matter. I don't want to go into the detail of the NMPDF, just to say that is a different kind of approach that you can use. So instead of having fixed functional form, you can have what we call non-parametrical functional form, which is not really non-parametrical, it's just a more general parameterization. And this is what I've been used for many years. Yes? Exactly. Yeah, you can. Because there is a much better theory on how to train a neural network rather than how to fit, you know, I will show you. It's intrinsic in the kind of error determination in the Hessian approach that you cannot go to too many parameters because it kind of breaks down the minimizer, all right? Because I show you. So because in a sense, the theorem that tells that the neural network can approximate any functional form is in the limit of very many neurons in the middle, okay? So you must have a lot of neurons in the intermediate layers, otherwise the theorem doesn't hold, okay? So that's why you try to go there. Yes, of course. Yeah, but the point I'm going to show is that basically most of these parameters are irrelevant, okay? So that's the thing. So when you fit that, what matters is not the parameters you get, it's just the kind of minimum and the configuration that gives you that minimum. And many of the parameters of the configuration are either 0 or completely irrelevant. So this, in fact, goes to the next point. Whatever. So you, again, you minimize this thing in real life, but that's what everybody does. You know, you have a covariance matrix with all the correlation between experimental data, whatever. But the point, which is exactly what you were saying, is that so when you have a big parameterization like a neural network, and you can also have it with when you have a big polynomial, Eventually you can fit the noise, okay? You can go through all the points and have all these wiggles between the points. So how do you know that you are not there? Okay, so how do you identify a proper training? And this is something that is known in data science. So the idea is that you kind of always split randomly all your data between two sets, a validation set and a training set. So the neural network only sees some data. And then when the chi-square, when the figure of merit of the training keeps going down, but actually the one of the validation stops going down and either grows or stays still, that's the point where you have to stop the training, okay? So, and that's the point that tells you what are the relevant parameters in the configuration, okay? So this is something that, in a sense, of course, you feel, oh, it's cool to use neural network or, you know, a large, but you have to be careful to these other sets of problems that you introduce. Very good. So this was the first thing. I'm just talking about parameterization. So how you parameterize the independent quarks, anti-quarks, and gluon. Okay. So what I told you is parametrical thing, a fixed parameterization, or a neural network, which is a bit more subtle. You can more easily vary the architecture. Okay. So these are the two parametrical and non-parametrical options. Now, the second point, which is crucial, is how you propagate the error. So how do you define the error sets that you have in an LHA PDF output, okay? Again, you can't do directly an infinite dimensional probability density, so you have to always project this problem into some kind of finite dimensional problem, okay? So clearly, if you choose the optimal parameters, you're already projecting the functional space into a restricted n-dimensional space where n is the number of parameters, okay? At that point, to find the probability space in the functional space is just to find the probability for the parameters. So you find the best fit for the parameters and the uncertainty for the parameters, and then you're done. Then you have defined the PDF uncertainty. It's just an uncertainty on a set of parameters, all right? So that's what is done in what we call the Hessian method. I'm gonna tell you in a second what it means. But to do that, you really must have a fixed parameterization, all right? The other method is to do a Monte Carlo sampling of the probability density in a functional space. So the idea is that you have some basis of your functional space, which is a finite basis, and then it's like a bootstrap method, what is called the bootstrap method in statistics. And then you basically, to find the average value of an observable in a functional space, you just average over the members of your Monte Carlo sampling of the function. Now I'm going to tell you how you do things in both cases. Because again, this is a different thing that different PDF groups do, okay? So the Hessian method is used by most PDF fitters, so CTEC, MSHT, HERA PDF, ABM. So you project the problem in an n parameter dimensional space, and you just have to use whatever minimizer. So it has nothing to do with machine learning. It's a statistics problem. So you just have functions that depend on whatever, 20 parameters, and you find the minimum, the global minimum of the chi-square as a function of the parameters. And then you take the shifts of this parameter around the minimum, and you always assume a linear approximation, okay? So you assume the linear propagation that any observable that is a function of this parameter, you do just a Taylor expansion around the minimum, okay? So this should be not 0, but should be A naught. I'm just shifting A onto A minus A naught so that the minimum is at 0, so it's clear what I'm saying. Then assuming the linear propagation, that's what you have, that any observable function of the parameter is the observable at the minimum plus this term. And then the variance for that observable is given by the covariance matrix in the parameter space. So you take any observable and you take the derivative with respect to that parameter. And the maximum likelihood is given by the Hessian matrix, that's why it's called the Hessian method. So the matrix of the second derivative at the minimum of the chi-square, okay? So this is something that we have all learned in functional forms. So basically the idea, this is, if you are interested here, it's explained in all details by Pampling et al. So you take the original parameterization, you diagonalize, so it gets a kind of nice circle. And then in the diagonal space, you do actually find your minimum. And then you define this surface where, the Hessian matrix is equal to something, okay? So you take back the contour of constant chi-square into the parameter space. Very good. So that's what you do. So basically at that point, the variance, instead of being the Hessian times the variation in all the direction of your eigenvector, is just the gradient of your observables calculated at the minimum, okay? Very good. So let me just give you, so this is the kind of, so in a sense, to visualize what I just said, So you find the minimum of the chi-square into the parameter space. Clearly, it's a much more complicated space because you need to have 20 or 30 eigenvector dimension. You find the minimum, you linearize around the minimum, you calculate the kind of second derivative, which gives a paraboloid in this space. And then you take delta chi-square equal to 1. It should be in kind of statistics book. And this gives you the uncertainty in the parameter space, okay? So then what you give to the LHA PDF users are the variations. So the central set is the one calculated at the best fit of the parameters. And then the error set are the sets computed at the plus and the minus variation of the best fit of the parameters. That's why the eigenvectors are always in pairs. So you have the central, then the plus variation, in one direction, the minus variation in that direction, and so on and so forth. So this is what is done. This is how you build the uncertainty into the PDF space, starting from the parameter space. Clearly here there is a controversy that is something that has been debated for 20 years since I remember, but it's not a trivial one because, this is the kind of textbook statistics, and this is done only by the ABM group because they say we only fit few data sets because we want to use textbook statistics. So we don't want to have a delta chi-square larger than 1. Instead, groups like CTEC or MSHT, they say we want to put all the data in, but at that point we have to account for inconsistency between data, which means that this delta chi-square is not equal to 1, but to some tolerance, okay, which accounts for the incompatibility of the data. Okay, so this is in a nutshell because I don't want to be pedantic because it would take too long, but just to explain a bit what is the philosophy behind the different PDF determination and what are the approximation that one has to do to use this method, which is perfectly defined from the statistics point of view, is really that the likelihood is described by a quadratic chi-square with this revised tolerance, delta chi-square equal to T. And there are methods to determine it by kind of estimating the degree of incompatibility between the data, okay? So this is a subtle point, but this is what is done. Yes? Yeah? Yes, and that in practice, you inflate the uncertainty on your PDFs by a factor which is T, square root of T, okay? In a sense, so if we were living in... Yeah, dynamical tolerance is simply a way to say that you inflate the uncertainty by different amounts depending on the direction. When it's a global tolerance, you kind of just raise the profile and you take a larger contour in your parameter space, okay? Yes? This is done by this diagonalization. Yeah, when they when they go into the orthonormal eigenvector basis, they have already diagonalize for the correlation. So this is the point where they simplify the correlation problem, okay? Okay, anyway, so this is one way. The other method that people was the one based on the Monte Carlo method. So Gile and Keller and Kosover, they had the first idea in 2001. So the idea was, okay, instead of choosing, again, you can choose a parameterization, but instead of doing the Hessian approximation, you populate the parameter space, okay? And you calculate the probability of the parameter values into the parameter space. That was the idea, okay? So the idea is that you kind of sample. Again, you can see where is the problem, because if you have 30 parameters to sample a 30-dimensional parameter space, you need a huge amount of replicas, okay? So that, anyway, that was the idea. So for 23 parameters, you need 10 to the 11 replicas. It was not feasible, okay? So again, this is the idea that the people who started the NMPDF collaboration had. They say, why don't we do an importance sampling? So instead of sampling into the PDF space directly, we sample into the data space. So we generate replicas of our experimental data. And then for each of these replicas of the experimental data that I show you how they're generated, you find the best fit for your PDF. And this gives you, so it's as if you project the Monte Carlo sampling from the space of data down to the space of the PDFs, okay? So this was the idea. And how many replicas do I need in this case? So basically with 100 replicas, you are accurate by 1/n, okay, 1% accuracy for your variance. And you need 1,000 replicas to be accurate also for your correlations, okay? But anyway, with 100 replicas, you are 10% accurate in the correlation in the sample and 1% in the variance. Okay, so that was the idea. So that you have your experimental data and you generate a multi-Gaussian distribution around your data. Where these are random number generator, which are normally distributed with mean around 0 and variance, which is the one that multiplies the experimental uncertainty, okay? So basically the idea is that if, let's say, you just have 2 data points, so these are the 2 data points and you generate okay, this is replica 1, so they oscillate up. Okay, so you have a distribution of data. If they're correlated, the replica points, they oscillate together up, then the next replica could be this one where this data oscillate down. So you basically create a sample in the data space, okay? Yeah, it's a separate treatment. So there is, again, here there are a lot of technicalities, but because of this D'Agostini bias, you have to treat the normalization uncertainty in a different way. And the statistical is here. These are the correlated, because you need to, if you have correlated systematics, you have to do this, what I just said, the data have to oscillate together by the same amount, okay? And this is what I said, with 100 replicas, that's 10, 100, 1,000, you get a good representation of your original data points, okay? That's what you want to have. You measure the correlation among the data and you check if with your sample you have reproduced them. Okay, so the idea is that, so you have, sorry, go ahead. Yes, yes. Yeah. So these are all generated with the covariance matrix, which at the moment is 5,000 times 5,000 data points. And indeed, another, the devil is in the detail, is the inversion of this. But you can do it. There are all, thanks God, there are lots of people who work in statistics. We can learn, but every time is a pain. You have to learn how to do these things. But anyway, it's feasible. You can do it. Okay, whatever. So you generate this Monte Carlo generation, and then fitting each of these instances of the Monte Carlo sample, you get the best fit in the PDF space. And this gives you a representation of probability density, okay? So what do I mean by that? For example, each of the green line is the best fit for a gluon given by that instance of the data. Okay, so and I could do this by parameterizing the gluon with a polynomial or with a neural network. You can choose. So in a sense, if you have a Monte Carlo method, you do whatever you want with the parameterization. You don't have to use a neural network. You don't have to use a parameterization. So in this case, this is a neural network, and you see it because each of the best fit has a wild different functional form. And this comes from the fact that the neural network is a redundant function, okay? And each of the green is the best fit. So then, if I have to tell you what is the average value of the gluon, then I just average over the green line at a given x, okay? And if you tell me what is the PDF, the central value for the W asymmetry, I take the 100 prediction that I have for my 100 replicas, and I take the average, and I take the variance, then I can give you all the statistics about the uncertainty that depends on the PDFs, okay? So I give you the full probability density, which means that this gives you whatever you want, okay? So an NMPDF puts together the neural network and the Monte Carlo techniques, but as I was discussing with Maria Vittoria, you can do different combination of these things, okay? Good, so these are the method, and whenever you have to use a PDF, you have to know what method has been used, okay? Because depending on whether a PDF set is done with the Hessian method for the error propagation or with the Monte Carlo method for the error propagation, you have to do different things, okay? So for the central value of a PDF dependent observable, here you take the observable computed on the central set, here you average, and for the Hessian, you do the usual variance formula for the plus and down variation in the eigenvector space, and for the Monte Carlo, you have to calculate the variance of a Monte Carlo set. Sorry, I forgot to mention that there is this JAM collaboration at Jefferson Lab, and it's interesting because they use Monte Carlo method, but with a fixed parameterization. So here you see two examples. The NMPDF uses the Monte Carlo approach with a neural network. JAM uses the Monte Carlo approach with a fixed parameterization. So these are interesting things to compare. Yes? Yes, it's avoided. I have it in the backup. I didn't want to spend too much time on an NPDF because I looked biased. But so now what we do is we have, one single huge network. So we have about 20 neurons here, or I don't know, 17 here. And we have 8 output, which are the 2 light flavor, and then this is the fitted charm, and that's the gluon. So they're all together the output of a neural network. So now we have even more parameters, okay? So what is done? So now we started really to use a kind of machine learning techniques, but the idea is always the same. We still split randomly the data into training and validation. And we use what is, again, something like stopping criterion with this clip norm that you have in TensorFlow. But anyway, it's just fancy words to say the same thing done more properly using all these Keras and TensorFlow stuff. And the other thing, which is crucial, is how do you choose the architecture? How do you choose the weights between the various things? So, because before we were choosing it, manually. So we were exploring different kind of connection, different kind of function. And now, again, we took from the data science idea, the idea of hyper optimization. So we run this thing many times on different hyper parameter set, which means different architecture, different stopping criteria. And we select the one that better generalize over unseen data. So we, on top of training and validation, we have test data which have never been seen, and these are used to define the parameters of the big network. Yeah, for that, hopefully, when you find the kind of final fit, you have to check the stability. So we found that you have to try to vary. So 75% of data in the training and 25% in the validation, or even 50-50 gives the same results. So you have to check the stability upon all these choices that you make. And it's not easy. I think that's a problem. It's not a problem. It's we did the best we could, but just something. Sorry, I don't want to take too long, but I think whenever you reach that level of complexity, not just with the NMPDF, but also with the other PDF sets, you have to try to do a closure test, is what is done in other. So you have to, let's see that we are God and we know what is the law of nature for the PDFs. So we should try to, what if the data are produced with non-PDFs? So instead of having real data, we have pseudo data that are generated believing that the truth is given by next to leading order QCD and, I don't know, MSHT PDFs, okay? These are the God-given PDF, they are true. So is my fit able to get chi-square equals 0 if I do 1,000 instances of those with 0 uncertainty? Then if I give the uncertainty, is my fit able to reproduce the uncertainty of the law of nature? So we spend a huge amount of time in NMPDF, but I'm sure that also the other collaboration to test this thing, okay? So this is something that before it wasn't done, but then at some point we realized that one should really be careful, to check the stability. So I think a closure test is always a good idea. Okay? Good. Yes. We vary the number of nodes in the intermediate layer and even the number of layers. You go from 1 to 3 in the feed forward perceptron. And the other trick is that here you put X and log X as if they were independent input, because the PDF have this structure which is exponential in the small x region. So if you were just training on X, the network would become crazy in finding that kind of behavior that you need for the small x part, where you have, sorry, not the exponential, the log behavior. Yeah. Exactly. Exactly. Yeah. If you want to look at the small x behavior of PDF, you have to plot in a log scale. If you want to see the large x behavior, you have to plot in a linear scale. This is somehow the kind of understanding of these kind of things. Okay? Any other questions? Good. If you have any question afterwards, I'm here. Okay, then I talked about statistical framework. I just gave you the gist of it and the experimental data. Now I want to give you what are the theory inputs that goes into a PDF fit, because here, again, we are in front of new frontiers that I don't want to go in too much details because there is only 40 minutes left, but and there are lots of things to talk about. So anyway, stop me if you have more questions, I will go. Okay, so the theory prediction, so that's the game. Now we always minimize the chi-square where we have the data, the experimental covariance matrix of the data, we all the cross correlation, and then we have the theoretical prediction, okay, where the theoretical prediction are the ones that include the PDFs that we want to fit. So you have F1, sometimes you have F2, and then you have sigma hat, okay? Sigma hat is computed at a given order, okay? So we have to make a choice for the theoretical accuracy of our prediction, and we have to be consistent across the board for all the observables that you include in a fit. So typically, the kind of standard global PDF fits are based on fixed order NNLO QCD calculations, okay? Already saying NNLO QCD calculation is super complicated because, imagine you have to vary this F according to your parameter 2,000 times every time you do an iteration of your fit. So you don't really put the NLO calculation. We always have to do interpolation grids to have a fast interface between the real calculation at higher orders and what you put in a fit. Okay, this is the people who developed Apple Grid or FastNLO, they did a great service to the community, because otherwise we would not be able to calculate NNLO QCD calculation so fast and so many times during the fit. Okay, so this is the kind of technical details, but I spent 1.5 years of my PhD trying to get this fast interpolation. So, you know, it's one of the details that you really need. And the other thing is that we have to choose all the parameters. The value of alpha S, it's kept fixed typically. The mass of the W, mass of the Z, alpha E, the CKM matrix elements, the heavy quark masses, branching ratio. So there are lots of things that are built in your fit, okay? Because these are the parameters that you choose for the theoretical prediction. And the other thing is that the missing higher order uncertainty that you have in the perturbative expansion is not included in the PDF uncertainty. Okay, so all the PDF uncertainty that you see until now is purely the experimental uncertainty that I talked to you about. So the one due to the fact that we have a finite number of information on that flavor at that value of X. But the fact that all the theoretical prediction that we use have a finite accuracy themselves at the moment is not included as a kind of standard. But this is the frontier that people are working on. Why? I think here it's because we have been, you know, because of the progress in theory, because the new frontier is n-cube below. So we already have a lot of cross-section that are known at n-cube below in QCD, okay? So for example, we had the gluon-gluon fusion, that was the first one. We had VBF, vector boson fusion. We had lots of, and also the W cross-section, the Z cross-section have now been calculated to n-cube below. So this is the paper I'm referring to. And now you can see that the PDF uncertainty, they have to cook up some recipe, because they say, okay, on top of the band that you give us and we get from LHA PDF, we have to introduce a new band, which is the green one, which is the one that is due to the mismatch between the theoretical accuracy of your PDFs and the theoretical accuracy of the partonic cross-section. Because remember the factorization, you have sigma hat and the PDF. If the PDF are computed at NNLO, and this is n-cube below, there is a mismatch, okay? So this is why the frontier is to either give ourselves what is this kind of theoretical uncertainty in the PDF, or trying to go towards approximated n-cube below PDFs, okay? Very good, and this is the same for the Higgs. Now, gluon-gluon fusion, you can see that on top of the PDF uncertainty as a function of the collider energy for gluon-gluon fusion, there is also this estimate. Okay, at the moment, this estimate is, I think it's overestimated, because they just take, you know, half of the difference you have when you do a fit with NNLO PDF and with NLO PDFs. They say if you go to the next order, you're gonna have half of the shift, okay? So this is what they do, what they use in order to calculate that, but clearly it has to be more sophisticated than that. Okay, so how do we estimate this mixing higher order in the theoretical prediction that we use in the PDFs? So this is a fit of the gluon at leading order, the gluon at next to leading, the gluon at next to leading. When I talk about that, I talk about the accuracy of the theoretical prediction. You can see that the leading order, basically, it's a horrible gluon, is unreliable. And in fact, it's used very often in the Monte Carlo, in the PTATU, and very often you use, anyway, whatever. So but anyway, there is a huge theoretical uncertainty going from leading order to next to leading. And then you evaluate what is the shift in the gluon going from next to leading to next to next. And this can give a measure of the theory error at next to leading order, okay? And then you compare to the PDF error at that given order. And you can see that as a function of x, sometimes at next to leading order, the theory error is larger than the PDF error. Now we are at the next order, but this is the thing that is telling us that we are underestimating our uncertainty if we do not keep that into account. So how can we do? Okay, here it can be really boring. No, not boring, it's fascinating, but it can be very technical. Okay, so there are three proposals so far that came out in the past 2 or 3 years for how to include missing higher order uncertainties in a PDF fit. Remember that we include a huge number of processes, and each of them has their own renormalization scale, which is process dependent. The factorization scale, you might argue that it's the same for all processes because because the PDFs all evolve the same. You can, again, this is something argued by people, but they say, because of the collinear factorization, you can say that the factorization scale among the 5,000 data points we have here should be chosen to be the same and whatever. So what you can do is that on top of the covariance matrix with experimental error, you can estimate a theoretical covariance matrix between theoretical prediction. How do you estimate it? You vary the factorization and normalization scale in all processes by a factor of 2, up and down. You can choose a lot of prescription, 9-point prescription, where they are all varied independently by a factor of 2, 7-point prescription. I don't want to bother you with the details. And I have to say that here there is a level of arbitrarity, if you want, in the model of correlation between the various processes. But just to give you the idea is that, so it's explaining this paper that we published 3 years ago. So if you just take a experimental covariance matrix, these are the experimental uncertainties. So you can see that there are some blocks because some of the experiments are cross-correlated. If you add on top of it the theory covariance matrix, you have much more correlation between all points that are in your fit, okay? But the other thing that you can think intuitively is that if a process has a large theoretical uncertainty, then it's de-weighted in your fit, no? Because you are adding the scale variation uncertainty, if you want, to the experimental uncertainty. So you're mixing up together how well we know that measurement experimentally and how well we know that thing in theory, okay? And they go together in this covariance matrix. And there will be soon some, okay. Now, the nice thing is that, okay, there will be a publication in a few months because so far we did it for NLO, but for NLO, it's nice because you can see that basically when you go from just theory uncertainty and theory plus, from just experimental and theory plus experimental, you see that there is compatible PDFs, but with larger uncertainty, but nothing dramatic. So there is not a factor of 0.5%, 50% that was in the previous plot. Anyway, I just want to give you the idea without telling you too many results, even because there aren't yet the results at NLO. Sorry. Yes, with NLO, that's why we did this. Was a proof of concept at NLO because we had the NLO PDFs and it does incorporate that central value. So that's a good thing. Yes. Yeah. Yes, exactly, within the statistics, yes. But I like it that there are lots of assumptions that I'm not sure if they're correct. I think it would be good to have different methods. Then, okay, I don't talk about that. This is something I did with one of my students. So you see all these colorful replicas, they're not just labeled by replica number, but also by scale. So you can pick, the different factorization scale and the renormalization for the different kind of processes, and you can do statistics on this bigger sample. It's not practical, but it's the kind of less biased than the previous approach. Or there is the MSHT approach. So you might have seen in recent conferences that there are these approximated NQ below PDFs by MSHT. So they started to include all the information we have about the next cube leading order, splitting functions, and matrix elements. And what they do is that the unknown terms in the next cube below theory are added via Gaussian prior, and the parameters are fitted from the data with the uncertainty. So this is something that it's good, but some theories don't like it, and because you don't want to fit the next order correction that you don't know from the data, because the theory and the data should be independent, okay? It cannot be too wrong, you know, in a sense, they did a lot of tests with that, but this is the idea, you know, so to add as nuisance parameters, the next order correction or the incomplete correction we have, and have the data determine these parameters, okay? And indeed, you can see that for the gluon, the approximate NQ below gluon is very different from the NNLO gluon. In a sense, so here it's expected because we know that at small x, the perturbative convergence is less well-defined, as we were discussing with some of you this morning. But here it's a bit weird. Anyway, there are lots of things that trying to investigate this thing. It's really a frontier, you know, it's something that I don't know the right answer. Nobody knows the right answer, but there are a lot of attempts that are very noble because it's important to fix, you know, this thing if we want to go into the right direction. Okay. And there will be also an MPDF, which is done in a different way, but I don't want to bother you with that. Okay. Some of you asked me about electroweak correction, so I wanted to mention that. So I only talked about NNLO QCD, but clearly if you go to NNLO QCD or even NQ below QCD, you want to have the NLO electroweak correction, because we know that, okay, it's not always true, but kind of as a kind of rule of thumb, you have the NLO electroweak correction are as important as the NNLO QCD corrections, okay? The thing that I want to point out is that on top of all this thing, virtual electroweak correction, real electroweak correction, that I don't want to enter that, but this creates, so you have to match what you are doing here with what experimental is doing the data taking. And this is something that is giving me headache for a year, but I'm trying to, so, you know, that's something that, and then you have the photon initiated processes. So what I want to say is that if you want to include the NLO electroweak correction, you do need to have the photon initiated contribution. So what you need to do, you need to add a photon to your DGLAP evolution. So on top of the quark and anti-quark and the gluon, we want to add QED corrections to the DGLAP evolution, okay? This is, sorry, I forgot to add the references, but there are some paper by Daniel De Florian, some people who do this thing really in a nice pedagogical way. I can send you some references for this, but you can see that basically it's the same idea. So this is the equation that you saw before. On top of the splitting of the gluon into gluon, quark, anti-quark, you have the splitting of a gluon into a photon, which you don't have. You have it at NNLO. Whatever. So you have all these terms that you have to add. Okay, so you have also the splitting function. They are expanded not only in power of alpha s, but in power of alpha s and alpha electroweak. Okay, and as you can see, for example, apart from the non-abelian component, which we don't have for the photon, it's a similar thing. You have just EQ square over CF. So at leading order, it's easy. When you go beyond leading order, it's more complicated. Okay, very good. So the fact that you're adding a photon here, it means that the quark and the gluon will change, because now their evolution is coupled to the evolution of the photon, okay? In particular, they will give up some of their momentum to the photon, okay? And again, as a function, so this is a Q square dependent statement, but you can see here that the fraction of momentum that the gluon loses in favor of the photon is about 1%. Okay, so this is the kind of more or less how much of the momentum the quark and the gluon give to the photon. It increases at larger values of x, and it's always within 1%. Okay, so the photon carries up to 1 to 2% of the proton momentum. Okay, so how do you determine the proton, the photon PDF? Again, there was something until some people had a clever idea. So there were two ways. Either you determine it from the data or from the theory, okay? So because from the theory, we didn't trust the modeling of the photon that we had in some old papers, so the idea said, okay, NMPDF, we are clever, we just determine it from the data. So we said, okay, what are the data that are maximally correlated with the photon? So the data that have a strong photon-initiated parton channel, so photon something parton channel. So for example, the high mass Drellian data, LHCb low mass Drellian, so all the Drellian data in principle can give us some information about the initial photon. But when we did the exercise, the kind of data-driven knowledge of the photon PDF, so treating it on the same footing as the other quark and gluon, you see that it's basically not determined, really. It has a huge uncertainty because the data don't give us enough information on it, okay? So, but then there was a theory breakthrough. There was the idea of the LUX PDF, okay? So there was this paper that by Manohar, Nazan, Salam, and Zandarig. So I invite you to read it because it's nice. So the idea is that QED is perturbatively known up to a very low scale. So the photon must be computable in theory if the input substructure is known. So the idea is that they say, okay, let's write the cross-section for a chosen BSM process, so the production of a heavy supersymmetric lepton in EP collision. And they wrote these things in two ways. So either just, with the form factor, so, you know, everything that you heard this morning is very relevant for this computation, or in the parton model, okay? And you equate these two things, and by equating these two things, you extract the PDF of the photon that you have here, okay? So what you have here is just the cross-section as a function of the structure function, which are experimentally known up to very good precision. You go nearly into the elastic limit, and here it's just the parton model formula that you saw earlier, okay? If you equate these two things, you calculate the photon PDF. So again, it's a theory-driven knowledge. So you can say that the photon PDF is equal to this thing that you see here, okay? So what do you need to calculate theoretically the photon PDF? You just need to have the structure function between x and 1. So in all the range of the structure functions, okay? Including the elastic form factors, which are in the elastic region. Anyway, whatever. So this is a formula, you put in what you know. At that point, you don't need a fit of PDFs to extract the photon PDF. You just need what is the experimental uncertainty of these two functions in the known region. And indeed, you can see that the photon luminosity now has a 1% uncertainty. Okay, so the only uncertainty you see here is the uncertainty on the structure function that you use to compute it theoretically. Because you need to have some input on the structure at low energy. So it's not completely theoretical, but I mean, so here we were trying to put into a global fit of PDFs, but because basically we are dominated by QCD, the information you get on electroweak parameters is super small, okay? So it didn't work. Instead here, you can read the paper, sorry, I'm really bad at explaining it now, but it's really like computing the same observable either in the parton model or in terms of the structure function of the photon. So either you try the proton as a whole and you just compute the cross-section here, or you use the parton model. By doing these two things, because they apply also at low energy, then you can find this formula over here, okay? So it's theoretically in the determination, but you still need an input, but which is much better known than what you find from a QCD fit of the proton, okay? Okay, very good. So thanks to this approach, now we can include the electroweak corrections. We can include the photon as calculated by these people. You can also add the data knowledge, which kind of gives you the same answer, but with a slightly smaller uncertainty, because now that we have an input which is not unknown, we can build upon it and refine its knowledge by using the data. But at the moment, to be honest, nobody has had the stamina to do, I don't know what happened. Nobody has had the stamina to do the full NLO electroweak and NNLO. So NMPDF is working on this. So we added the photon, it's gonna be published soon, but we have not added the electroweak corrections in full because of this problem of experimental definition of final state radiation. Okay, I don't know people who work on electroweak things, they know what I'm talking about. Okay, so yes, any questions? No? Good. So here I just wanted to give you a kind of table that maybe you can go back to on, everything I said is in this table over here. So there are different data. So this was the status June 2022, okay? Hopefully still valid. So you have these three collaborations, which are the kind of global collaboration because they include most of the data that we have available. But again, within each of these green tick, you can see that there are different choices made. For example, an LHC vector boson and top. But anyway, you read the paper and I have something in the backup. And then the statistical treatment here I showed, Monte Carlo versus Hessian dynamical, Monte Carlo, blah, blah, blah. Parameterization here, I'm giving you some you will recognize something that I mentioned. I didn't have time to mention the heavy quark schemes because it would deserve a lecture just to talk about it, and I don't have the time. But again, there are different ways of treating the heavy quarks as well, and also the order at which the fits are performed. Okay, so this is a kind of table that should allow you to understand a bit the differences. So let's look at the different determination. I just focus on, okay, yeah. So there was a golden age, 2016, where all the PDF collaboration were living in peace and happy all together, and there were no fights at the conferences because everybody agreed on the gluon, Exactly, the fights were the people who were not in the plot, exactly. They saw that there was a conspiracy theory to get exactly the same gluon at the same mass, okay? But at least there was peace among the global PDF collaboration. Then this peace was soon over, and that's the situation now, 2022. So you can see that, that's the white papers, no mass. Okay, I think, yeah, it's the same axis. So you can see that, okay, again, let's say that we don't believe in Atlas because they only have the Atlas data, and sure. But even the other collaborations, they do give quite different results, especially, so as far as the gluon is concerned, at least they all agree, but you have to decide which uncertainty you want to believe in, okay? And some people say that NMPDF 4.0 with all these fancy deep learning techniques is over-aggressive in terms of uncertainty. You see what they mean here because the uncertainty is much smaller than the other collaborations. And NMPDF would reply, yes, but you have inflated your uncertainty by a tolerance factor, whatever. So, but at least now when you see that, you understand there is a tolerance factor, there is a methodology that is more or less aggressive, there is a different parameterization, there are different data that go into it. Yes. Yes, MSHT did, because they increased the parameterization because they didn't fit with the data. CT18, this set does not include the very constraining W and Z data from Atlas because they cannot fit it in this set. They have a special set that fits this data but excludes the jets. So it's really complicated. So in a sense, now people fight again. I think it's healthy because I think they still try to understand the differences, but you know, we need new data to try to generalize, to understand better who is right, in a sense. If the uncertainty is underestimated, we will understand it as you add new data, okay? Mm-hmm. Yes, so for example, here ABMP has a fixed polynomial with three terms in the interpolation region between small and large x. CT18 has a Bernstein parameterization, but they have a larger tolerance. And again, they go up to the third order in the Bernstein polynomial. So it could go farther, but it doesn't go as far as it could go. So there are lots of technicalities. But because it's difficult to find the minimum, you know, all this thing of the Hessian, you have to find the minimum in an n-dimensional parameter space, and it's not easy, you know. You have to be careful not to have degenerate minima. It's so you cannot add as many parameters as you want. Anyway, it's ongoing studies, I think. There was a recent email by Andy Buckley. They want to, so they say if there are young people who have the stamina to try some, yeah, that was exactly, I can forward it to you if you're interested. There are some people who are trying some alternative method to all of these to try to see if there is a truth, you know. Anyway, it's not easy. Okay, anti-quark, it's similar thing. And yes, and here you can see that really, you know, if you want to compute cross sections at the LHC, and these are, for example, sigma Higgs and sigma TT bar Higgs, they are correlated, right? Because they depend on the same PDFs in the initial state, some of the flavor. Okay, so that's why you can see that these are not circles, these are ellipses, but you can see that depending on which data set you use, you're gonna get a different estimate of the PDF uncertainty. So NMPDF 4.0, which is these ellipses, gives a very precise prediction. But then you can say it's too small, whatever. If you take MSHT, you get this prediction. You know, I think this observable is still fine. There are some outlier, and we know why. But in a sense, the percentage of the uncertainty is quite dramatic. So there is a dramatic difference. If you look at TT bar and Z, it's larger, so and in fact, okay, that's not the plot I should have showed you. But for example, the mass of the W now, the Atlas determination, they get a number for the mass of the W if they use an NMPDF 4.0 or 3.1, whatever. And if they use another set, they get a number which is farther away from it than the nominal uncertainty on the W mass from Atlas. So I think we are at the point where it's very important to understand who is right, which one is the best treatment you can give, okay? Because otherwise the W mass uncertainty from Atlas is twice as the one that they declare in the latest paper. So that's why there are a lot of benchmarks and things that we are trying to understand. That's why we did our code public, so that everybody can use it and in PDF and find bugs. So if there are bugs, it's in a sense, but I think everybody should do something to make their codes public, because it's a point where for the community, it's important to understand these differences and love the truth more than oneself, I think. Okay, anyway. That's it. Okay, I don't know if I have time, but I wanted to say something that is really dear to my heart, that has to do with what I mentioned at the very beginning. So how can we relate PDF fits and new physics? Because remember that everything that we do, not only collinear factorization, but we always assume the standard model, okay? Of course, if you do a fit of the PDFs, the sigma hat, they're always computed in the standard model, okay? What if there was something more than the standard model? So this is an old idea that, so for example, the CTEC group, that it's some interesting study where people still believed in light SUSY, that, you know, if you were turning on the LHC, you would observe SUSY. So you say, okay, what if I add new colored partons to my protons, okay? How would they modify the DGLAP evolution, okay? And how would they modify, in this case, alpha S running? Because if you have colored states, they would also modify alpha S. And this was used to give some bounds, and the comparison that they did in this very nice paper excluded any light colored partons even before not observing them. Okay, so it was higher than LEP limits, okay, at the time. Okay, then something that I did with one of my students and Matthew, my colleague at CERN, was what if instead of having colored states, okay, which are clearly not possible, what if you had a colorless state, for example, a dark photon? Would there be room inside the proton for a dark photon? Again, you do a very simple thing. So you just do, you calculate the splitting function, which are exactly the same as the QED splitting function, and you do a power counting of what order in terms of the dark photon coupling you have to add into your DGLAP equation. And then you calculate using the momentum sum rule, how much room you have for it. And okay, I don't want to go into the details, but it was nice to see that it does give some bounds on the mass of the dark photon and the effective coupling, which is, okay, only in few regions, but it's competitive with the other bounds that we have from other kind of experiments. So I think that this is just an idea, but one could do some axiom PDF. So, you know, some of these weakly coupled partons, one could still do studies that are interesting and could increase our understanding of new physics. The other thing which I learned recently, so what I showed you at the very beginning is that because we don't know very much the large X PDFs, the high mass Drellian tails, which are the ones where people look for deviations in the tail. So if you have some, you know, imagine that you have some distribution. If you have a bump, you see it here. But if the bump is farther away, you would just see a slight excess in the tail, okay? This is what Ilaria told you in her lecture of this math. But these tails are affected by a large PDF uncertainty, okay? So you need data that constrain the large X to see and characterize new physics. This is the point. And in this case, I think, so how do you go to large X? So you either go to low energy and large X because you look at things at different angles. So for example, the EIC will have a very large coverage of the large X region at low energy, or you take the data that are at very large energy at the LHC, okay? Okay, so I should have explained this better, but I think, so what I tried with my group in Cambridge, we said, okay, let's imagine that there is some new physics in some high invariant mass scales of Drellian distribution. We are always talking at the high Lumi LHC because these are kind of the scenarios where, okay, good. So imagine, for example, that there is a UV completion of the standard model that has a W prime with the mass of 14 TeV. So you don't produce it directly, but you would have a bump beyond, maybe at the FCC. Okay, we wouldn't see it here. This deviation that is induced by this new particle would show in the high Lumi LHC Drellian distribution at large invariant mass, but we wouldn't see it because they have large PDF uncertainties, okay? So we wouldn't see that there is a deviation because it would still be within the PDF uncertainty of that observable, okay? Now, because we are greedy, we want to have constraints on the large X PDF, we take this data and we put it into a PDF fit, okay? Because we use this data to constrain the large X gluon, okay? But we do a standard model fit. We use the standard model to generate an NLO QCD prediction. My belief when we started this exercise with Michelangelo Magno, I thought, definitely, we are going to see that there is something wrong, okay? We are going to see that the chi-square for this particular data that are generated using the UV model, but using the standard model is going to give us a bad chi-square. Instead, what we find is that the distribution of the chi-square is perfect, for all the points. And what happens is that we get the same good data theory agreement, we get a good fit, so we wouldn't spot any sign of inconsistency, but the anti-quark at large X shift. So this would be the UU bar DD bar luminosity. The one that we find with the 14 TeV MW prime would be this one, would be far outside the PDF uncertainty, because the anti-quark PDFs at large X compensate or fit away the effects of new physics in the high tails. So this is something that, if you're interested, you can read this paper. But to me, it tells you that really you need to have not only a high energy program, but a low energy one. Otherwise, if we just try to get everything from the high energy data, so new physics, math fits, and PDFs, we might run into these problems of fitting away signs of new physics. And I think that's interesting. Okay. Yeah, the other thing that I wanted to mention very quickly, I know that I abuse of your patience, is that, you talked about, I think Ilaria said that she mentioned it, so I just wanted to tell you. So in the SMEFT, you have all these sets of operators, you have global fits of SMEFTs. The thing that is interesting is that many of the fits, of the data that are used in these MEFT fits are the ones that are in the kinematic plane that I showed you before. So they're also used in PDF fits, the very same data, okay? So the JETS data that go in this analysis, the DiJETS data, the top pair production data are not just used for this MEFT, they are also used to constrain the PDFs. So, and clearly there is an inconsistency because when you do a SMEFT fit, you keep the PDF fixed. So theta are the parameters of the PDFs, and you just vary C. When you do a fit of the PDFs, you set C equal to 0, you determine theta. Okay, so there is always a kind of orthogonal search, one for the theta parameter, one for the C parameters. But what if there were correlations between the two? And this is what we started to do with some of my students in Cambridge, because what we're interested is, sorry, what are we doing? So in principle, you should tell me, why do you want to care about the interplay? In a sense, PDFs are low scale physics that is separable from high scale physics. However, the complexity of the LHC environment might intertwine them because we're using the same data to extract both, not because the PDFs are a high energy effects. So what we're trying to do is, can we do a simultaneous fit? So this is a mess because already doing a fit of PDFs is a mess. Now you add more degrees of freedom. But actually we managed to do it by using a neural network with an extra layers that fits the parameters that you want to fit at the same time as the PDFs. And these answer some of the questions that I list there. So the first one, how to make sure that new physics are not inadvertently fitted away. And then how would the bounds on the Wilson coefficient that you have in the SMAP fit change if I was consistently using PDFs that include this effect? And whatever, so we found that, for example, the problem is that you can always do it for some test scenario. You cannot do 2000 feet plus the PDF. So you can always restrict yourself to some kind of new physics. But if there was some new physics that shows up into the Drellian tail, as we can imagine from the other fit, you would have a much larger PDF uncertainty when you do a simultaneous fit and a larger bounds for the Wilson coefficients. When you do it for the top, you find the same Wilson coefficients, but you find the PDF with a larger uncertainty that accommodates the PDF without the top data and the PDF with the top data. So I think it's all very interesting. If you want, we can discuss about it more. I wanted to say something about intrinsic charm. I don't know. I don't think I have. Okay, do you have the stamina to listen to 3 slides about intrinsic charm? Yes, you nodded. So you're brave. Okay, good guys. Okay, so the charm of the proton. So again, the common assumption that we do in PDF fits is that the static proton wave function does not contain charm quark. So the proton contains intrinsic up, down, strange quarks and anti-quarks, but no intrinsic charm because the mass of the charm is larger than the mass of the proton, okay? So how do you produce it? You produce it dynamically through the gluon evolution, okay? So the gluon evolves, and when it reaches a threshold, which is of the order of the charm mass, it splits into charm, anti-charm. So somehow the charm distribution is always totally correlated with the gluon distribution, okay? So if the charm is perturbatively generated, the charm PDF is trivial. But actually, there were Stan Brodsky, who just did several papers about, there are models that do predict an intrinsic component of the charm, okay? So the proton can have a much more complicated wave function structure that has an intrinsic charm component. And if you believe that, then your charm would have a perturbative component and an intrinsic component, which is the one that would be there. Yes? Mm-hmm. When you speak about the target part, no, in fact, we don't put this model in. We don't put this model in. What you do, what they did, I was not involved in this paper because I didn't have time. I didn't contribute to this, but you can see that what they do is that they fit the full charm and they fit the perturbative charm. What is left is the intrinsic, okay? So the idea is that how can you disentangle the perturbative charm component to the fitted charm? And what they find that you can see in this paper is that actually it looks as if the charm agrees with the model by Brodsky. So Brodsky was very happy about this result. But again, yeah, so behind this result, there is all the methodology that I talked to you about, okay? And there are lots of details. But just to say that this is another hot topic because, for example, CT doesn't believe in this result, and with different parameterization, you get different results. But anyway, so this is a paper that I think it's interesting. It created some controversy, and now there are, I can't say more because I didn't work on it, but I think it's, again, different methodologies can give you different results, okay? Also about kind of fundamental questions about the structure of the proton in terms of an intrinsic charm component. No, That's also, there is another thing about if PDFs are positive or not. But at that scale and at that X, PDF don't have to be positive. It's just a cross-section have to be positive. You can have negative PDFs. It's not a physical quantity. Nobody tells you that the PDF in a given scheme, it's a scheme-dependent, yeah. It's a scheme-dependent quantity. So Stefano Forte says they are positive above 5 GV. Collins says he's not right. So there is another thing about PDF. Yes. So sorry, you're right. This is at I think I don't know. I think it's 5 GV square, but I don't want to bet on this. Have to. Exactly. Yeah. So in a sense, both of them have this behavior at small x, but what matters here is not very much the behavior at small x, it's the behavior at larger intermediate x. Yes. So anyway, this is something that we will hear more in the future. So I wanted to give you some update. And I just want to say, that was something that Wu Tung said in 2000. And I really like it because, we are here in 2023, we're saying the same thing. So he said, after 2 decades of steady progress in determining the parton distribution function, has global QCD analysis of parton distribution function reached the end of the road? Or will the physics challenges of the next generation of collider usher in the dawn of a new era with fresh ideas and more powerful methodology? I think this is something that we can ask ourselves even now, where it seems that everything is understood. Instead, clearly, from 2000 until now, we did a lot of progress, and I'm sure that more progress can be done also thanks to young people getting involved in this effort. Thank you very much.
So I'm not exactly sure because my experience was quite time back. But I think there is some notion after some gymnastics that we can actually compare different priors to each other. So if you would choose your fixed form of the polynomial as the direction of one question, can you actually then choose whether, for example, the first line is then better suited compared to some other form?
Yeah, in fact, the problem is that in all this, so we are all doing a kind of frequentist analysis, no? If we determine the parameters and their uncertainty. So we don't do a Bayesian determination of the parameters, I think, no? And this is what I'm trying to understand with some of my collaborators. Can we have a different kind of answer that comes from a kind of Bayesian? Because in that case, you would have a much clearer understanding of how the prior influences the posterior. Because clearly with the polynomial parameterization, that's your prior, okay? But you cannot vary infinitely. In a sense, it's not practical for the collaborations, to keep varying. We could do a exploration of the parameter space and to see what they get. But again, it's not done in a Bayesian way. It's not that the prior is updated because, what are the range of the parameter before doing the fit? It's not clear, no? So if you instead had the Bayesian approach, you would have a clearer mapping. Also with the NMPDF, we don't have a clear understanding on how what is the prior that we put in the architecture, and so, but how do we distribute it? There are lots of little things in the initialization of the nodes and stuff like that. So it would be nice to do it in a more Bayesian way, but I don't think we have yet a methodology to do that.
Then also, right, then now at PDF, so you chose this architecture just because it was working once, or do you have like a guiding principle on how you do it?
No, it's what is called hyperparameter optimization. So what is done here? So you look, you scan the space of architecture, and so it's a huge. It takes a lot. Okay, we did a lot of carbon emission by doing that, but okay, it hopefully was useful because you have to take. So what we do is what we call a k-fold. So you take all the data, you divide them in several folds, and you use a test set of data. And we chose the architecture and parameters of the neural network that improved the k-folding and the generalization to the test data. So we didn't choose the one that has a minimum chi-square because this would give you overlearning. We chose the one that better generalized where we don't have data. Clearly, this is a very advanced thing. And also in machine learning things, there are always papers on how to improve that. Again, we scanned the finite number of parameters, but still quite a lot. And there was, the final choice was the one that had a clear, better behavior as compared to the others. Did we find the best? I'm not sure. The best that we could find. Yeah. Yeah, maybe someone can come up with a different kind of neural networks to do the same job. I don't know. There could be other kinds of networks that one could use, I'm sure. But we restricted ourselves to this perceptron network.
Thanks. Benchmarking exercise where everybody use the same that's what happened.
Yeah, it did happen. Actually, it was published. I think I did not update my slides. Yeah, I should have said not ongoing, but yeah, this is the kind of thing, so that's the benchmark. So we all took the data from MSHT 20, CT18 prime and MPDF 3.1 prime. And you see, now we agree on the quirk, but the uncertainties are different. So still, an MPDF has a smaller uncertainties, and the other have larger uncertainty. And this is down to the methodology because we still use the tolerance, we use the hyper optimization. So, but at least it tells you what is due to the methodology, what is due to the data. So it was a very useful exercise.